Hey y'all, this is going to be quiz 11 version 1, and what we've got in this one is we've got a rigid insulated container. It's fitted with a paddle wheel that contains 5 pounds of water. Initially we're going to be at a temperature of 260 degrees Fahrenheit, and we've got a quality of 60%. Alright, so that means we've got that liquid vapor mixture there, and the water is going to be stirred until our temperature goes up to 350 degrees Fahrenheit. So for this water, what we want to do is we want to determine the work in BTU, and then we also want to find the amount of entropy produced, and the units for that will be BTU per degree Rankine. Alright, so let's start with part A. Okay, so with part A, what we want to do is first, let's notice that this is a rigid insulated container. We don't have fluid going in or out, so we're just going to use our basic energy balance equation. So let's write that out. Alright, so we have that. And then let's see what we can cancel out. Are we going to have a kinetic energy here? Nope, so that goes away. Do we have any height changes? Nope, that goes away. And then what about Q? It's insulated, right? So anytime we hear insulated, that means we're going to ignore Q. Okay, so that leaves us with delta U equals negative work. All right, so let's kind of restructure that, and let's rewrite it as work equals negative M times little u2 minus little u1. And let's call that equation 1. All right, so now we've got our equation 1, and now let's see what we can do. Okay, so we're going to start off by finding our values at state 1, where we're at 260 degrees Fahrenheit. All right, so let's do that first. So let's find U1 first. So U1, if we use our equation with quality, will be 1 minus the quality at state 1 times UF at state 1 plus X1 times UG1. All right. So for these two values right here, the UF1, UG1, we're going to go to the tables for that. And the table we're going to use will be A-2E. All right, so let's fill everything in. So we're going to have 1 minus our quality, which is 60%, so we want that in decimal form, so put it as 0.6. And then UF1, let's go to our table. All right, so this is table A-2E. Our temperature is 260. All right, so then we come over here to the internal energy, right? So this is the UF column where we have saturated liquid. So that's going to be 228.6. And then we also need UG, so that one's in this next column, so 1090.5. All right, so let's put those in. All right, so 228.6 and then plus the quality, which is 0.6 again, times the 1090.5. And this gives us a U1 value of 745.74. And units for that will be BTU per pound. Okay, so this is our specific internal energy at state 1. All right. And now let's go ahead. I'm going to go ahead and find V1 because we're going to need it in just a second. So V1 will be our specific volume. We have a very similar equation to this. We're going to have 1 minus X1 times VF plus X1 VG. All right, and these are all at state 1. So we're going to use the same table we used before to find VF and VG. So if we do that, we'll have 1 minus 0.6. And then I need to find my specific volume over here on this table. So 260, we come over here, we got 0.01708, and then 11.77. So let's plug those in. All right, so there's VF, and then plus 0.6 times 11.77. And that's going to give me 7.07. And that's cubic foot per pound. All right, so that's V1, our specific volume. And the last thing I want to find is entropy at state 1 because I'm going to need that for part B. Okay, so let's go ahead and do that. Same equation we had in the previous two things, except for now instead of U or V, we're going to have S for entropy. Okay, so we're going to have 1 minus 0.6, and then I need the entropy at state 1, so we'll come over here, 260, we get 0.3819. All right, and then the SG value will be 1.6864. So let's plug those in. All right, so 0.3819 plus whoops, wrote that wrong, plus 0.6 times 1.6864. And that gives me 1.1646, and the units will be BTU per pound degree Rankine. All right, so now I've got that. Okay, now remember part A, we're wanting to find work here. So some of this stuff we need for part B. So now let's see what we need to do to get work. So I need U1, which I already found, and then we need U2. I haven't found U2 yet, I need to do that. Okay, so to do that, let's draw this little picture. So let's say that's T, that's our specific volume. If we draw our little vapor dome here, let's say we're at state 1 down here. All right, so that's at 260. State 2 is going to be at 350 degrees, right? So that's going to be up here in that superheated vapor range. All right, so this is 1 and this is 2. And notice I'm drawing these directly on top of each other, right? So just a vertical line connects these two. And that's because we've got this rigid container. All right, so since it's rigid, our specific volume will stay the same from, state 1 to state 2. So that's why we're drawing this vertical line. So for state 1, we were down in here, and then state 2, we're going to be up here in the superheated vapor tables. All right, so now let's find U2. Now, at state 2, we're going to be at a temperature of 350. All right, so we got 350 degrees, and we already know V1 is going to equal V2. All right, so that means V2 is going to be 7.07 cubic foot per pound. All right, so now, using those two pieces of information, the temperature and then the specific volume, we're going to be able to find U2, and then we're also going to find S2 because I'm going to need that in part B. All right, so let's see what we need. All right, so first we're using table A-4E, all right, because we got the superheated conditions now. Now this one is a little bit different on how we're going to do our interpolation. All right, so if we look at this table, let's look at 350. All right, now remember what our V value is. Our V was 7.07, right? And that's all I know. I don't know the pressure or anything like that. I know the temperature, I know this V value. Okay, well if you work through the tables, you will see that we have to be in a pressure around this range, okay, because this right here is our column for V. So at 350, for a pressure of 60 psi, I have a specific volume of 7.82. If I increase the temperature to 80, my specific volume, whoops, pointing at the wrong thing, my specific volume is going to go down to 5.8. Okay, so I've got to be somewhere in here. I don't know the pressure though, right? So we're going to kind of do a weird interpolation thing where we're going to use our value of V and relate that to U and then S. Okay, so let's see what we're going to do. And let's pay attention to these values. I got 7.82, 1121.4, and then I've got 5.8 and 1118.5. All right, so let's write up here what we're going to do. So what we're going to do is we're going to take the difference between the U values that we know. All right, so we're going to have 1112.4 minus 1118.5. And then I'm going to divide that by the difference in V, right? Because V is really the only parameter that I know other than temperature. So I got to relate everything to V. So we're going to do 7.82 minus 5.8. Okay, so now I got that. And then on the right side, I need to get my new value that I'm wanting. So for that, I'm going to use the values here. So I'm going to do 1121.4 minus X. This is the U value I'm looking for, so this will be U2. And then I'm going to put that over 7.82 minus 7.07. All right, and then with that, I can solve to get X, which will be 1120.32. That is U2. And the unit would be BTU per pound. Okay. So a lot of the times when we do interpolation, we're going up and down in the chart. Here we're going, across the pressures. So kind of a different way of thinking about it. So this gives me U2. I can find work right now, but let's go ahead and find S because we need that, and we're already here with the table, so let's do that next. All right, so we're going to do the same thing to get entropy. We're just going to use these values here in the last columns. And again, we're going to relate them to our specific volume because that's what we know. All right, so we're going to have 1.683 from right here minus 1.6476. We're going to divide that by 7.82 minus 5.8. And then we're going to set that equal to 1.683 minus X, where X is going to be the entropy at state 2, and then we're going to divide by 7.82 minus 7.07. And then if we solve for X, we get 1.6699, and that is S2. And our units, will be BTU per pound degree Rankine. Okay. So now we got all this stuff figured out. Now we can finally get the values we're actually looking for. So let's find work. All right, so work, we're going to use this equation 1. Okay, so we're going to have negative times the mass, so it'll be 5. And then we're going to have 1120.32 minus, because this was U2, minus U1, and U1 was way up here, 745.74. So that gives us a work of negative 1,872.9, and that's going to be BTU. All right. I left out my units here. Remember, this is pounds, this is BTU per pound. So the pounds are canceled. So this will be our work. All right. And then lastly, we got to do part B, which is find the amount of entropy produced. All right, so for that, we know delta S equals the integral from state 1 to 2. We're going to have this delta Q over T B plus sigma. All right, so here Q, we don't need to worry about all this. So that goes away. And that means our sigma is going to equal the change in entropy. And remember, this is capital S. So that means we can rewrite this as M times little s2 minus little s1. All right, so specific entropies here. And we already have all these values we need. So plug everything in. We got 5 pounds. And then we have 1.6699 for S2. We found that right here. And then we subtract off S1, which is 1.1646. And the units for both of these are BTU per pound degree Rankine. So pounds cancels. And that gives us a sigma of 2.5265. And there we have it. So there's our sigma. That is the amount of entropy produced in this system, going from state 1 to state 2. All right, guys, hopefully you like that one. I'll see you for the next one.